please stick around for the discussion after my talk. So I want to kind of talk about salts and wrap them up across the solar system. So this morning we had a discussion about brines, predominantly here on Earth and habitability there. We talked a lot about Mars in this session. I will also talk about Mars, but also thinking into further across the solar system. So here I have two images. On the left is Columbus crater on Mars, and it's one of these great paleo lake examples. You can even see the salt ring deposited as a bathtub ring as it evaporated. And then on the right, Europa, which I'll talk a little bit about as well. So first, very briefly, if you're in this session, you probably know about salts, but chlorine salts in particular have a wide variety of flavors. We have chlorides, which is just Cl-, all the way up to the highly oxidated perchlorate, ClO4. I'll just note that hypochlorite, that's bleach, NaClO is bleach. Chlorite, these are both they're not very stable, so they're mostly intermediate processes into the formation of chlorate and perchlorate, which are fairly equally stable. So during formation, you end up with both chlorate and perchlorate in about equal amounts. Everywhere you find one, you find the other in just about equal amounts. So the three salts that we're most interested in are going to be chlorides, chlorates, and perchlorates. And the reason that it's really important to distinguish between the different types of chlorine salts and the different types of salts in general is because they all have a different effect on the activity of water, freezing point, and just the general stability and habitability. So here you can see a table of different salts and their eutectic temperatures, which is just one of many things that affect habitability. But obviously when we start talking about the solar system, getting to temperatures where water can exist, that's kind of, step zero, step one. And sulfates and carbonates, which have been the predominant salts found across the solar system on Mars, Europa, they don't lower the freezing point as much as chlorine salts do. And you can see here, as has been much talked about in this session, calcium perchlorate down here at the very bottom at 198 Kelvin. But you can see even some of the other magnesium chlorate and perchlorate, calcium chloride, etc. Going up here, magnesium sulfate, a much favored salt on both Mars and Europa, seen in a lot of places. It only lowers it by 4. So it doesn't extend the stability range as much as some of the other chlorine salts. And then, of course, chlorine salts can also be a source of energy. Here's just a diagram to kind of visually represent this. So, of course, on Earth, we have pure liquid water, freezes at 0 C. It boils at 100, unless you live in Flagstaff like I do. And then it boils at 93 Celsius. And this is exactly why the stability on Mars is so reduced, because the boiling point is dependent on pressure, the atmospheric pressure. And so on Mars, the boiling point is only 10 C. However, if you look at a eutectic composition of magnesium perchlorate, you can get freezing temperatures down to minus 67 Celsius, and you actually also extend the boiling temperature up to 24 C. So you're really extending the range of stability in both directions for temperature. And just for comparison, this would be like magnesium sulfate. It doesn't extend the boiling point at all, and as I mentioned, only 4 degrees below pure. So another example of why salts are so cool is this deliquescence thing that everyone's been talking about. So here's a video of it. This was taken in the chamber at the University of Arkansas, and this is magnesium perchlorate. You can see it's actually, fairly humid, it's fairly warm, and I will note this is an 18-hour time lapse. So as we start over from the beginning, you can see that the droplets start to form almost immediately, but it does take, over the course of 18 hours, you still don't have all of it deliquescing. And this is at a very high, much higher than the deliquescence relative humidity that we've seen in some of these other talks, and a much warmer temperature. So even at these relatively benign conditions, it still takes almost a day for the majority of the salt to deliquesce. So thinking about whether life can even utilize these salts or tolerate, there's been a lot of discussion in the Earth community about that. Microbial community has been found to thrive in magnesium chloride-rich brines. This was down to an activity of 0.63. I will note that they found sodium and sulfate in there as well, so that could have a mediating effect on this magnesium chloride. So again, activity is not the end-all be-all determination for habitability of the brines, but still having them, seeing where we can extend the limits. We've seen bacteria metabolize down to 18% NaCl and minus 25 C. And then one of my favorite stories to tell in this picture here is halite crusts. And so this Davila et al. 2008, I'll go back one, here, went to the Atacama Desert and measured basically how many times it rained in a year. And they found that it rained once. And so that was about 6 hours total of liquid water event. However, in these halite crystals, we've talked a lot about deliquescence. This is just NaCl. The deliquescence relative humidity is 75%. So the amount of times that it crossed 75% relative humidity was 57 times. So 57 events where there was liquid inside these halite crusts for the microbes to utilize that water versus one event of rainfall outside of it. And then there's examples of perchlorate and chlorate reducing bacteria. So chlorine salts are pretty interesting and potentially tolerable to some sorts of life. So where have these chlorine salts been found, in particular perchlorates? So they've been measured by the Phoenix mission, by the Wet Chemistry Lab, and then in Gale Crater by Curiosity. On Earth, as mentioned, they are pretty rare, in fact, accumulating only in these hyper-arid environments like the Antarctic, Atacama Desert, or the US Southwest, and they tend to be formed by oxidation. So how do we find them unless we actually send a mission there? And so one way would be through remote sensing. And if you look at the spectral comparison of different hydrated salts, here on the left you have in green, so first I'll say this is the near infrared from 1 to 2.5 microns and reflectance on the y-axis. In green you have epsomite, and in purple you have bischofite. So you can see that the spectral features are actually very similar to each other, and this is because you're looking at a magnesium ion wrapped with 6 or 7 waters, and then the anions are actually outside of it. So you're actually really looking at hydration state. That is the dominant feature in the near-infrared spectra of different hydrated salts. And then again, on the right here, you can see gypsum, which is a classic spectrum. Everyone who sees a spectrum of gypsum goes, that's gypsum. Except magnesium chlorate, 2H2O, also has this triplet at 1.4 microns, and it also has a really weird 1.9 feature. There are differences. I'm not saying that one is necessarily being confused for the other, but when we go send missions to other planets, we need to be very careful to have enough resolution and looking at the context to understand and make sure that we're seeing the right salts. So to that end, I've been re-looking at some classic salty spectra. As I mentioned before, there's a Columbus crater here on Mars. Again, you can see the very nice bathtub ring, and here's a zoom-in image of it. And if we zoom in even further, again, here's that bathtub ring, and we can map the water, the hydration feature, that 1.9 micron feature, and start to pull out what some of the interesting spectra might look like. Thank you. So we can see that there's a lot of variability, even when we just look at anything that has a hydration band. And so, again, here, this might be one of those ones that people say, aha, it's gypsum. So if we zoom in on it further and we can start to compare it to other salts that have similar features to it, and then what we're trying to do is actually create some new parameters that will help us identify and distinguish between the different salts. So since I have less than 2 minutes to go now, I'll quickly move on to the outer solar system and just say that temperature also affects the spectra. And you can see here there's 3 pairs of spectra: magnesium chloride 2H2O, 4H2O, and 6H2O. And we have the 80 Kelvin, which is Europa relevant temperature, and then the room temperature one. And I'll just maybe zoom in on this little area here. You can see that at room temperature, it's kind of more of a shoulder, whereas at 80 Kelvin, it's actually a triplet and more of a real band. And this is, again, because, as I was saying, you have the magnesium and you have 6 waters octahedrally coordinated to it, and you're actually seeing the pairs of vibration. So you're narrowing the features as you go to colder temperature and really starting to resolve the individual features to it. So thinking about Europa, there's been a lot about the non-icy component, which would be these red regions on the right. And long story short, some telescopic observations were done using that laboratory spectra that I just showed, and they found up to, on the right here, 35 weight% of magnesium chlorine salts in the non-icy regions, and about 15 weight% of magnesium perchlorate. And then, so the perchlorate and the chloride are actually not necessarily co-located, but typically in the non-icy region. So to summarize, thinking about how to find chlorine salts, which of course will help us elucidate the habitability of any planet that we're going to, spectral libraries are needed at a range of hydration states, wavelength ranges, and temperatures to be able to actually identify these salts. And yes, I said all that, so I'll just go on to the summary, which is that the chlorine salts do tend to be globally distributed on Mars. We've seen them across different ranges, and we do think that we can actually start to identify them with our new spectral parameters. Europa's non-icy, non-sulfuric acid component likely includes chlorine salts, and it's important to differentiate between the chlorides and perchlorates, between chlorine salts and sulfates, because all these salts have vastly different effects on the habitability and stability of the liquid water. Thank you.
Time for questions for Jen, if anyone wants to come up. Does anyone dare?
You said she was all powerful.
Exactly.
Murti will risk it.
I think I can withstand. Hi, Jen. Murthy Gudipati, JPL. Wonderful talk, and also the video that you showed in the, let's say, vetting, or what is that?
The deliquescence.
Yeah.
Mm-hmm.
Do you think that grain size will also play an important role in the spectral properties?
Absolutely.
And
I did not mention it. I should have. Absolutely.
Yeah. If so, I want to pitch in here that there's an excellent graduate student from Alicia who has built an instrument in our lab where we are trying to do grain size dependent spectroscopy under radiation for any kind of icy material.
Sounds great.
Hi, I'm Marshall Stachinsky from University of Washington, and I just wanted to thank you for going into the detail about the salts at the start, because part of the joy of AbSciCon is I'm not an expert in salts, and this is a session that I wanted to go to because it's something that I wanted to shore up some of that gaps in my understanding. So those sorts of things are very helpful for me, and I'm sure I'm not the only one.
My pleasure. Thank you.
And with that, let's give her a round of applause.